the organizers for the opportunity to come here. It's been absolutely phenomenal experience and very humbling as well. And so, changing gears a little, I'm just a simple-minded experimentalist, so we'll be focusing more on pragmatic issues. And be talking about the self-assembly of optical metasurfaces, which I'll define in a second, but just a little bit of background. I'm a National Research Council postdoctoral fellow at the Naval Research Lab. And so if you're an American grad student looking for a good postdoc opportunity, the NRC is a good chance to do independent research. So I highly encourage you to go after that. And since we have an international crowd here, if you're not familiar with the lab, the best way I've heard it described is a government-run university. And so if you read the American newspapers, you think, well, that might be a train wreck waiting to happen. But historically, they've produced two Nobel laureates, a ton of good science, and a lot of practical applications. GPS was invented there, for example. And so these are my collaborators at the lab. And another note, a lot of the themes of this work actually started back in Kent in my dissertation with Peter Palfy, who, to the best of my knowledge, was the first one who started to talk about this connection between liquid crystals and metamaterials. I guess I don't need. So I'm interested in developing metasurfaces composed of nanoparticles with some unique sensing functionality, whether that may be optical, chemical, or electronic. And so the way we want to do this is essentially by bringing two nanoparticles close to each other, but not too close. And but not too close is really the trick to the whole story. And by doing this, we can tailor the permittivity and permeability of the material. So how do you actually go about doing that? And so there's two strategies. There's the top-down approach, where you're actually removing material and whittling your material down. And this is what's dominating the field right now. It's great for proof of principle, but if you're ever going to get the throughput to actually go out and use these materials, we really need another method, and that's bottom-up or self-assembly. And there's lots of nice advantages. Obviously, the throughput. You can get the nanometer resolution you need to get a lot of these optical properties and all these other great attributes. And so what we need to do is we usually start with a dilute suspension of nanoparticles, in this case spheres, that have been capped by some ligand. And we need to use self-assembly to assemble these macroscopic materials with these nanoparticles, and using the ligands to actually keep the nanoparticles separated from one another. So the way we go about doing this is we came up with a technique where we initially start with a suspension, in this case of gold nanospheres in water, and then some thiolated ligand of our choosing and a water-miscible organic solvent. We take the two, we dump them into a vial, and we shake it up. And this is what we get. And so this is about a 10-minute video sped up, and so this is our initial reaction suspension. This is the air-fluid interface. And you can see in about 10 minutes, we pull all the nanoparticles out of the suspension up onto the side of the vial. I'll let it run one more time. You can see it actually becomes clear in the bottom, so we actually pulled nearly everything out. Right, so what's going on? So this self-assembly process actually combines three aspects. We phase transfer our nanoparticles and functionalize them with a ligand shell. We self-assemble them into macroscopic monolayer films, which I'll demonstrate in a second, and it can transport them onto substrates. And so our initial suspension is gold nanoparticles, thiolate ligands, water, and the water-miscible organic solvent. And because we've used the water-miscible organic solvent, there's a high surface area. So our thioligands bond very quickly to our gold. And as soon as they're capped on the surface of the gold nanoparticles phase separate to the air-fluid interface. and we start to see a gold film appear at the interface within a couple seconds. And because we use two different solvents with two different vapor pressures, the organic solvent evaporates faster in this thin film relative to bulk. So this creates a surface tension gradient, and this pulls our film up the side of the vial. And so within a couple minutes, we've functionalized all our particles, and we've assembled them into monolayer films. And so this is what we get. So instead of the side of the vial, I can put a glass substrate in. And I hope you can tell on the left side what I've done is I've taken the film and I've backlit it, and then I've tilted it to catch a reflection from the overhead light. So the left side is the film in transmission, and the right side is in reflection. And the left side, hopefully you can tell that it's a nice blue color, hopefully, and it's not scattering the light, so there's not a lot of excess ligand. The right side, it's a gold-like reflection, so obviously it's very high density. And we can examine these films with SEM, and locally we have very good positional order, and the interparticle gap is essentially set by the length of the ligand. But the punchline is we have these macroscopic monolayers. And it's absolutely monolayers all day long. You can scan with the SEM till you're absolutely bored. And there's no multiple layer regions or some coffee ring-like effects. And so we can measure the absorbance of these films just with a white light spectrometer going normally through the films on a glass substrate. And these are the absorption curves that we get. So this is a dilute suspension of the nanospheres in water. This is it of the film. There's a significant redshift that just comes from capacitive coupling between the two, and it's obviously a couple hundred nanometers because we have approximately a nanometer gap, so it's a very large shift. But the quality of our resonance peak is remarkably well preserved given the high density of the films. And then from the absorbance measurements, we can calculate the effective imaginary part of the refractive index from these films. In terms of the real part of the films, I use a spectroscopic Mach-Zehnder interferometer, and I place two lenses in one arm of the interferometer, so it's actually confocal. And then I can translate my film into this region near the focus, and I can image the film, so the beam is probing half the film, and then the other side it's probing essentially just the air and glass. I can measure the phase difference to our first order maximum on both sides and calculate the phase difference between essentially the air and the film. And then to determine the sign of the phase shift, I have a liquid crystal wave plate in one arm of the interferometer. And by applying a voltage, I know how the fringes should move with the liquid crystal, and I can determine the sign. And then once I have all that, I can study as a function of wavelength, and I can back out what the effective real part of the refractive index is for the film, and I can build up a picture for this film. And for this particular one, the film approaches positive near zero values, in the optical regime. And so to make the connection a little closer to the liquid crystals, you can do the same self-assembly process, but in this case, we're using nanorods. Is that clear to everybody? These are little rods stacked end to end. They're aligned mostly in the plane, so they're planar alignment. But if you pay close attention, you can actually see domains where the nanorods are actually pointing right at you. So they're homeotropic, essentially. And so this got us thinking, could we play around with this and actually get them all homeotropically aligned? And it turns out we can if we're careful about things. So this is, the black curve is an isotropic suspension of the nanorods. And this is just like within a liquid crystal. You get one absorption peak from your longitudinal absorption mode and one peak from your transverse. And we're probing normally to the glass surface. And so this is the absorbance curve from the film. And you can see as the nanorods point towards you, you see less and less of this longitudinal peak and more and more in the transverse. So macroscopically, it's pretty good evidence that we actually have a homeotropic aligned film. And what this really translates into is building sub-wavelength diffractional optics. Turning more to chemical sensing environments, because we can create such small gaps in between these particles, much closer than top-down techniques, these are really good candidates for surface-enhanced Raman scattering substrates. And so if we functionalize these nanospheres with benzene thiol and essentially irradiate them with just a normal Heaney laser or something, the local electric magnetic field can be something like 100 times greater in this gap relative to your probe. And so long story short, essentially the molecules get very, very hot. They radiate like crazy, and we can, again, record it with a spectrometer, and it gives us this molecular fingerprint of the vibrational modes of this particular molecule. And so as a way to compare how good these sensors essentially are, this black curve down here is the Raman modes for just a neat suspension of benzene thiol. And in this measurement, we probe about 10 to the 14 molecules. Now, if I go and I measure the SIRS response from the film, it's about an order of magnitude bigger, this red curve, but we only probe about 10 to the 7 molecules. So we're probing 7 orders of magnitude less molecules, but we're actually getting a bigger response. So this enhancement factor, which I'm just defining as the intensity measured relative to the number of molecules probed for the film and the neat solution, actually ends up being approximately 10 to the 8th for these films. And one side note, it's very important where you calculate your enhancement at. If you use a vibrational mode near the thiol bonding, it can skew the polarizability, which will then skew your enhancement factor. So we chose this carbon-hydrogen WAG, which is this 998 peak, to stay far away from here, and it's got a nice strong signal from the neat suspension. And so we can, for each film, we can measure a surface averaged enhancement factors just from 10 random points as a function of nanosphere diameter and probe wavelength at this 998 peak. But the punchline is, from these self-assembled films, we have surface average enhancement factors comparable to state-of-the-art ones produced by top-down methods. And I guess my time's getting short, so 3 punchlines. We have this technique to create these metasurfaces. We developed this method to measure the effective refractive index, and we have these SIRS films. Thank you very much.
Is there any attempt to this type of surface, this enhancement effect for NMR?
Not that I'm aware of, no. Yeah.
Okay, thank you very much.